Please welcome to the stage, from the National Institute of Standards and Technology and the University of Colorado, physicist Jun Ye.
Hello, everybody, and good morning. And I'm very excited coming today. In 20 minutes, I'm going to tell you a simple story, I hope, of making a clock. And this is a clock made of atomic clock, made of light. As you can see on the screen, these atoms are bathed in light. They are attracted by light. Their atomic states are prepared by light, probed by light, and then read out by light. This type of atomic clock right now has the best demonstrated performance among all atomic clocks that exist today, and is based on the most fundamental understanding of light-matter interactions, building on modern atomic physics, quantum science, laser technology. And this is really allowing us to push the absolute frontier of measurement science. With the best clock like this, we can explore the very basic space-time fabric, the very basic nature of space-time fabric in the universe. But it also allows us to actually see the intricacy of a microscopic world, how very simple quantum mechanical laws governing how two particles come together to interact will give rise emergent phenomena in quantum world of many particle physics. This is what we heard about actually just a moment ago from Stephanie, interconnections between complex particles, complex parts. And in fact, the very notion of uncertainty is a very much important aspect of making a clock. I want to make a clock that's accurate for you. And my clock, in fact, does have many particles in there, as you can see. I want to imagine myself as a little Alice in the quantum wonderland, understanding how all these different atoms are interacting with each other, and yet being able to tell you the time at the level of 1 part per 10 to the 18 accuracy. Clock, of course, is very important, and the clock technology is everywhere. And that's because time and frequency is the most precisely measured physical quantity. So any other physical quantities, being pressure, temperature, length, and so on, we like to convert into frequency to make a very precise determination. And that's why clock technology has a very big impact on advanced manufacturing. Of course, one of the most well-known applications of the clocks is in navigation, whether it's spaceborne or whether it's ground-based. And the importance of clock for national security, for national defense, can never be overstated. We are also now on the verge of being able to synchronize clocks that are remotely located to a level of 100 times better than the currently possible. Imagine a clock from New York City and a clock from Los Angeles can run within a picosecond of each other. That will certainly defeat any fast day traders in the stock market. And we are also at the verge of being able to map out the gravity field of the Earth and giving you unprecedented level of accuracy of equal gravitational potential on the surface of the Earth down to a level of just a centimeter or so. This is the incredible technology allow us to trap the entire Earth, how the continents and the water tables are moving around, and so on. Of course, clock also has tremendous applications in the fundamental and applied science, whether you are building the next generation advanced light source, or building a vast array of radio telescopes that are all phase connected, or building satellites that try to discover gravitational waves coming from distant black holes. So we all know that clock has two basic ingredients. It has to have an oscillator that gives you a periodic motion, and you have to have sort of a gear mechanism for record keeping. An optical clock has a very, very direct analogy to that. Our oscillator is an ultra-stable laser, a laser that's being held in my hand, and you can see this green light. In fact, actually, we use those type of lasers, the wave that's emitted by the laser, as our pendulum, as our clock here. But lasers are man-made, and it's guaranteed that you can make a laser, I can make a laser, they probably will not agree. But we do have something that was made by the universe, atoms, that's been in existence for the last 15 billion years. And so they have no issues left over. Any issues have been settled a long time ago between them. And so we use these atoms as a so-called atomic reference, or the reference of the nature, to guide our laser. And the final tool that this being able to keep the record is a very new technology that we develop. In the next few slides, I will show you one slide that demonstrates the technology of so-called optical frequency comb that allow you to actually keep track of extremely fast light ripples. That light is oscillating 1 million billion cycles per second. How do you keep track of that with electronics? And that's the technology we have. And that basically forms the basic ingredients of an optical atomic clock. What kind of atom do we use? Here's a periodic table. Over the last 5 decades or so, the so-called microwave atomic clock, or the current international definition of second, is based on cesium atoms. My favorite atom is a strontium atom, on the second column of the periodic table. And there are many, many reasons going behind of picking a particular element, atomic element, for making a clock, obviously. But I'm going to tell you just one most important ingredient, why we pick strontium. And if you look at on the screen, there's a Bohr's model, which means that electrons, as they're circulating around nucleus, have so-called quantized orbits. Those orbits have energy associated with them. So when electron jumps between these different orbits, there's energy difference. And that's basically the atomic frequency we are trying to slave our lasers onto, reference our lasers onto those atomic frequencies. Those electronic orbits can be visualized as electron cloud around the nucleus. And electron cloud oscillates at a very fast speed, basically around the time scale of, again, 1 billionth and a millionth of a second. So it's oscillating at a femtosecond level. If you allow me to slow down that oscillation by a factor of 1 million billion times, then I can use an analogy of a pendulum, which oscillates basically 1 time per second. Okay, so I'm going to make that analogy. And if you see that this oscillation happens, and the attractive property of strontium is that this oscillation has an exceedingly long lifetime. The lifetime is so long, if I were able to have this clock really oscillating in front of you at a speed of 1 million billion times slower, then it can be oscillating over the entire age of the universe. It would never slow down. And that's why we pick that atom to make our clock. However, you may ask, after all, these electron cloud is oscillating so fast, how do you actually keep track of it? And you have to build extremely good laser to do it. And in this very simple animation, what I'm trying to show is that if you have a laser with its frequency perfectly matched with the electron cloud oscillation frequency, then you will actually be able to track of it, because every time the pendulum swings to the left, the bulb on the left shines up. Every time the pendulum goes to the right, the bulb shines up. And imagine these frequencies are not matched up, then what you will see is basically chaos. And this demands, because of the oscillator of the atom is so good, it demands the technology development of exceedingly good lasers to be able to keep track of these kind of atomic oscillations. To give you a sense of how good the laser actually is, imagine that we shine our laser from this podium to the surface of the moon, and the distance is about 0.8 million kilometers. And it takes about a couple of seconds for the light to get over there. Our laser is now so good that during this entire transit time, we can keep track of every single oscillating period of the light wave. It's about 10 to the 15 waves between Earth and the moon, and we can keep track of every single one of them. In fact, we have been making advances, and this kind of precision is already, giving an analogy again, is already as if you're measuring the distance between Earth and the moon, and yet you can determine this uncertainty down to a size of a bacterium. But we have every reason to be very optimistic in the next 5, 10 years. We will be able to extend that technology such that we can actually shine light from the Earth all the way to the sun. That takes 8 minutes to go there. And yet, in that 8 minutes, we can keep track of every single peak and trough of the light ripple. And this is amazing. You're not talking about light that has billion cycles, and yet you know every single one of them. And that's the accuracy of 10 to the minus 18 that I'm talking about. Imagine technology like this gets into space. I know NASA people get very excited by those kind of stuff. Because imagine you have satellites which are flying apart millions of kilometers apart, and yet you can keep their relative distance down to a fraction of the optical wavelength. And that's just amazing technology we'll be able to do in the next few decades. The laser is becoming available. And fortunately, here's the next technology that we cannot decimate such amazing frequency stability or phase stability of a laser, of a single laser, to the entire spectrum of electromagnetic visible landscape. And this is actually Nobel Prize winning technology of so-called optical frequency comb. Our lasers, our femtosecond lasers in the laboratory can emit this beautiful rainbow color. And if you zoom into the spectrum, it turns out it's got a very digital spectrum of optical frequencies. And these comb-like structure have very regular spacings from each other. Just by counting the frequency spacing between these regular comb structures, you will be able to dictate the frequency relationship or phase relationship between the red light or a green light. And I can directly visualize with data to show you the phase coherence of a red laser and a green laser. This is a technology that didn't exist 15 years ago. This is as if I have made a gigantic gearbox for you that connects different parts of electromagnetic spectrum. One part could be red light. The other part could be the green light. And when I say phase coherent, it means that when the gear starts to move, every single tooth of these gear is accounted for. Or another way of saying, every single ripple of the wave, whether it's in the optical spectrum or in the radio frequency spectrum, is completely accounted for. It's a very big reduction gear, 1,000,000 to 1, because the frequency ratio between microwave and optical frequency is about 1,000,000 to 1. But we cannot completely keep that under control. And I know DARPA is very big on this. We have seen this, if you go to the demo hall, you see this huge banner. We control the whole entire spectrum. We actually heard about this yesterday from one of the DARPA program manager. And I do say that we are very optimistic that we'll be able to control the digital frequencies starting from the visible landscape, going out to infrared microwave, going up to the ultraviolet, and eventually to the X-rays. Entire electromagnetic spectrum will be phase coherently controlled. This is the powerfulness of building the modern optical atomic clock. It's more than just telling you the time. It's about controlling the entire electromagnetic spectrum. So I have to tell you a little bit about the story on the side of matter. And the time is relative, as we know, and Einstein told us of relativity. If in this room, the molecules are moving around with a speed basically like a bullet train. So if I want to make an atomic clock with the molecules or atoms contained in a jar sitting at room temperature, these atoms are moving around with a speed like a bullet train. And it's really fast. And that's a problem. Why that's a problem? Because Einstein told us from the general theory of relativity, there are two issues when you're trying to make a clock. One is the local gravitational potential of these atoms will give you different times, depending on the relative potential difference. The second, if the particle is moving extremely fast, when I say extremely fast, actually can be just on the walking distance and the clock will slow down. And that's something we can actually measure in the laboratory. And so moving clock slows down, as we know from Einstein's relativity theory. So if I make a clock just using atoms that contain in a jar, that obviously will fail, because every clock will give you a different time. The time is completely relative, and this gets some people really angry about it. What do you mean? But this is something that we actually measure in the laboratory, and I can speak from the data. So that's not what you want to do. And here I'm going to give you yet another technology, and this tells you how fast this field is moving. Here's another Nobel-winning technology called laser cooling. In fact, Steve Chu was our energy secretary just a few years ago, but before that, he was a physicist. He was doing physics. The cooling atom, the basic idea is the following. In this jar, these atoms are moving extremely fast. And if you can tune the laser frequencies just right, and shoot lasers from all 6 directions, orthogonal opposing directions, you can actually, the laser can track these atoms, cool them down to a temperature about just a 1/1000th of the room temperature. It's amazing technology. You can actually look at those atoms with your naked eye, and your nose is about 1 inch away from these atoms, and you are sitting at room temperature. These atoms are 1/100000th of room temperature away from you. So these atoms are not very, very cold, and they're no longer moving around. You do not have to worry about the relativity effects at that moment. And you'll say, OK, Jun, build me a clock now. Turns out there's another physical effect you have to worry about. And sorry for this maybe this is the most technically detailed slide, but it's actually a very simple slide for many of you, especially for people who are doing the service in the military. It's a common experience. When you shoot a gun, as a bullet exits the gun, you feel a recoil. And this is something atoms feel. After all, we're using photons to probe atomic states. We're shooting photon machine guns at these atoms. So when the atom absorbs the photon, its atomic state is going to switch. So the photon gets absorbed, then the atom starts to move because of a recoil due to the photon momentum. And here's a problem. Why that's a problem? Initially, we were hoping to be able to measure atomic states and match the frequency very accurately with the laser frequency, with the photon frequency. But because this atom is moving, has kinetic energy, this energy has to come from somewhere, from this photon. And that means photon frequency, instead of directly matching with the atomic frequency, you have to give a little bit more energy to the photon to make that process go, to have energy conservation. And that little energy is error in experimental measurement, is uncertainty Stephanie talked about. And that's not something we want. So we have another tool, which is to chain up all these atoms together and with a strong spring force. If the spring force is stronger than the recoil momentum, then you can shoot a lot of photons against those atoms and they will have no recoil. But many of you sitting in the audience will immediately respond with a question. Now these atoms are being shackled. They are no longer free. How can you be sure they will tell you the truth? And turns out we have another laser trick. Here's a laser beam that you can actually focus into the middle of the vacuum chamber, just like an optical tweezer. You can actually hold atoms very gently at the middle of the laser focus. In fact, we can engineer the laser such that a shape like this, which is a ball, and very, very cold atoms are sitting in the bottom of this ball. But we can engineer the laser such that the trapping potential, the ball-shaped trapping potential, looks exactly the same in the shape and the form between the 2 clock states, whether it's in the ground state or the excited state. So this is the best free lunch you want to have. Because on one hand, you can hold these atoms up, can hold them there. Put those atoms in the ball, made out of light, invisible trap. And then in the middle of the vacuum chamber, just holding there. But on the other hand, you don't have to worry about the very act of holding these atoms will degrade the frequency accuracy of the clock you're building. And with technology like this, finally we can put thousands of these atoms trapped in this web of light. And in fact, we can putting them into this cartoon type of structure made out of light. And these atoms are sitting there, thousands of them, each one of them representing a 1 pendulum clock, imagine. And you can measure all thousands of these clocks at once. That's why we cannot get down to the 1 part 10 to the 18 level. For useful reference, it might be good to show you a historical chart of the performance of atomic clock since World War II. We know the microwave clock is coming down over many decades, and the remarkable performance improvement. And this is the technology that everybody relies on now, GPS, your cell phone, and so on. But it's hitting in some level of barrier, technical barrier, just simply because the quality factor is not as good as the strontium atoms I was telling you about in the optical domain. And this is the optical technology, this violent single-trapped ion, the strontium atoms in our laboratory. And at the moment, we cannot achieve a level of performance at the level of 2 times 10 to the minus 18. To just give you a quick sense of how good 2 times 10 to the minus 18 is, if you, again, use the universe lifetime as analogy, if we had that clock at the beginning of the Big Bang, it would not have lost a second till now that we are sitting here. Another way of saying, if I have this clock shrunk down to the size of a wristwatch, If I raise my arm by just 1 centimeter, the time will change. That's the powerfulness of relativity. Now, it's very much an abstract concept. It's something that you can directly watch and measure. And of course, my clock is not as small as a wristwatch at the moment. It's basically as big as two or three optical tables because it's a research clock. But I know DARPA would love to have that kind of a clock shrunk down to the size of a wristwatch. And there are people working on it. So I think this presents another opportunity. And yet, I want to really celebrate the most recent Nobel Prize to physics awarded to our colleagues Dave Wineland and Serge Haroche for their remarkable achievements of controlling single particle quantum state to the level for quantum computer, for precision measurements. What we have done is extend their technology to multiple particles. If they can do with 1, and we can do with 10, then we can do factor of square root of 10, 3 times better, as long as we can control those states to be exactly the same. And that's actually not a trivial aspect of controlling atomic interactions, because if you're trying to squeeze thousands of these particles into a little, very small, compact space defined by the light, they're going to interact. They may be very weakly interacting, but still they will influence the atomic accuracy. And this is something we have been working for the last 6, 7, 8 years. And in fact, those papers reflect those efforts of trying to understand these atomic interactions, this emergence of complexity. And if you don't understand this, you will not be able to build clocks at 10 to minus 18 level. But then I would argue this actually lies an opportunity. The opportunity is the following. Imagine that I have 5 of those pendulums. Instead of making them individual measurements statistically independent, such that I can average them over by 5 copies, and you gain precision by square root of 5 because it's white noise. Imagine I make those 5 pendulum to be quantum correlated, such that you can treat off those 5 pendulum as a single quantum entity. Now you have only 1 unit of quantum uncertainty compared to the 5 pendulums, so your uncertainty will go down as 1 over 5 instead of 1 over square root of 5. 5 is a small number, but if it's a 5,000, if it's a 5 million, the square root of 5 million versus 5 million is a big difference. And that's where that's why we are very, very optimistic that this 10 to minus 18 is just a temporary achievement at this particular time, 2015. And I certainly think in the next decade, wonderful opportunities of quantum technology will flourish, and the clock will just continue to advance. I think with this, I'm concluding my talk, and I want to really congratulate DARPA for its tremendous role that's nurturing this type of science. And I know that I benefited, and many, many of my colleagues in NIST and other areas have benefited from strong support of DARPA. And what's important is I was supposed to build an atomic clock. But in the end, we can actually study many particle physics, how quantum phenomena emerge from simple rules of quantum mechanics governing just 2 particles. Now you put a 3, you put a 4, you put a 5. As a physicist, we like this kind of a model, being able to really understand every single step as the complexity becomes bigger and bigger, and we can track it. And this is really the essence of the quantum information science as well. So building a clock ended up being able to gain insights for advanced material, quantum information science, advanced metrology. Who knows, in the next decade or 2 decades, we may be able to finally understand room temperature superconductivity, and that will be tremendous for our energy use. Maybe we'll finally be able to build a computer so powerful that understand protein folding, that we'll be able to have shared entangled states, quantum states among different planets, that will have a quantum communication that's so secure that in principle you can never break, and so on. I think the opportunity is tremendous, and DARPA has played a very leading role in fostering this kind of science, and thank you very much. And also I want to thank you for your listening, and finally, I'm ready to take your questions, but I want to give credits to people in our group and just put their smiling face on the screen for you. Thank you very much.
Thank you. Fascinating talk, Jun Ye. Thank you. I'm Rick Weiss again, Director of Communications at DARPA. I'll be moderating the questions for our last few plenary talks today. We've just got 5 minutes for questions for this session, but that's like a bazillion femtoseconds, so don't feel rushed. If we don't have anyone at the microphones right away, I've got a couple that have come in online. Do you believe there are any fundamental physics limits to timekeeping? That is, can one keep slicing time at finer and finer intervals, or are there only technical limitations, or are there natural limitations?
That's an excellent question. Actually, we actually pondered about these questions from time to time. As far as I can see at the moment, I think there's no particular technical limit that would limit us. A few years ago, we were saying, the clock is actually always limited by so-called black body radiation, which is the temperature of your laboratory is a finite temperature and has a photons at the black body, which comes in, actually shift the clock frequency just so very tiny bit. But you can measure that. It's a technical problem you can completely solve. Maybe the problem is when the photon comes in, hits atom, the photon is now buried inside this atom. So if you think about it, the atomic mass, in fact, is heavier, yeah? Because the photon has energy. Energy is a mass. The photon is buried inside the atom. Atomic mass is higher. So maybe that can lead to some atomic frequency shift. But this is the effect we can know very, very well from physics, and we can account for that. So again, that's not a problem. Maybe I think the limitation comes from the fundamental physics itself. Certainly we know if you push to 10 to minus 33, you will hit this limit so-called Planck time scale, where everything finally is quantum mechanically fluctuating. Well, that's a huge long ways from us. I think before we hit that, we'll see some other very, very interesting physics. For example, if you get their clock to 10 to minus 21 or 10 to minus 22, your clock will be very, very noisy because suddenly, wherever the distant galaxy has a black hole exploding, that gravitational wave will influence your clock. I would love that. You turn your clock into this incredible sensor to hear the heartbeat of the universe. Is that a limit, or is that a new instrumentation for physics? It's great.
So next time I'm late for a meeting, I'm going to blame it on some black hole somewhere, kind of throwing me off. Okay. Are there any physical or technological timekeeping milestones that would open the door to new scientific tests or applications? In other words, if we could achieve 10 to the 20th precision, we could then test for something or do something.
Yeah. So, as I said, at 10 to minus 18, we can already at the level of being able to measure the geoid at 1 centimeter, the equal potential of Earth's surface. If we can go down to 10 to minus, but it's still not as sensitive because the clock is sensitive to the potential, not local gravity. Suppose underneath this podium, we have a gold mine. Can I bring my clock and then find out there's something that's buried under me? It's not as sensitive yet as gravimeter, which measures the local gravitational acceleration, gravity. But if we go another factor of 10, then that story changes. You would be able to track motions of water. Maybe you put clocks around the volcano. Actually, one important issue that we were talking with a guy from National Intelligence of Geophysics, I forgot now, it's the Geology National Intelligence Agency. And they say, for example, Yellowstone is very dangerous. Is it possible you put clocks around it and you will know how the mass is moving underneath our continent, and you will be able to tell whether there's something that's going to erupt, make a prediction. By the time you go, and that's 10 to minus 19 will have impact. 10 to minus 20, 10 to minus 21 is where I said earlier you will be able to see gravitational waves. And as you keep going, we're testing. There are a tremendous amount of uncertainties right out there. This is a great opportunity for being a physicist. We say dark energy, dark matter. That's because we don't know what's going on, and we call them dark. And a clock like this, when you go out there, put space satellites, put clocks up there, you'll be able to explore these very fundamental questions, cool. Let alone those usefulness for national security purpose.
Fantastic. Mike 1.
Charles Cerny with the Air Force Research Laboratory. I'm wondering if you postulate on the question of precision time, is there a thought also that maybe the field of quantum adiabatics may be coming into play? Systems that may be reversible because you're able to measure the precision time and look at that trace.
This is actually, I think it's actually a very complex question that you're asking. Well, maybe we can come down to what is the definition of time, yes? If it's something which is completely coherent, going back and forth, then the time is not defined, whether it's going forward or backwards. You play the movie forward or backward, they look exactly the same. And so we'll completely lose whether we are at the beginning of the universe moving forward or we are just going backwards on the universe. But there is, of course, real time. That's the entropy, the law of thermodynamics, where entropy is always increasing. And this is something, dissipation will come in. There's a fundamental quantum fluctuations. In the classical world, there's no noise, and the noise always comes from quantum fluctuations. Finally, you put multiple particles together, they interact. This is a very complex question. Then that will give rise to the forward direction of the evolution of the system. And indeed, the clock is actually playing that role in that we can understand 10 particles put together in a box, have them interact. One particle had a spontaneous emission event. How does that influence the phase diagram of these particles interacting with each other? And I think that role of understanding microscopically many-body interaction complexity, I think a clock can play a big role.
Thank you.
Thank you for that question.
Weirdly, we are out of time. So
sorry.
thank you very much.
Thank you very much.